in the last several videos, we have been considering that time is suspect. We found that for a moving clock, it runs more slowly than an identical clock at rest. We've also discovered that, according to Einstein's special theory of relativity, based on his two postulates, that length is also suspect, that, as we have here, length contraction occurs along the direction of motion. So if you have a moving object going by you, as you see it go by, and you measure the length of it as you watch it go by, you will get an answer, the length from your perspective, from your frame of reference, looking at that moving object going by, will be 1 over gamma, the length of that object, if it's just sitting there at rest next to you. Or if somebody is on that object, if it's a spaceship or a train car or something like that, they will measure one length for it, the rest length, sometimes actually called the proper length. It's not the greatest term because it sounds like that's the correct length and everything else is incorrect. But the proper length, or perhaps rest length, is the length of an object while it's at rest. Okay? And so if it's a train car and somebody is riding along in it, as far as they're concerned, remember, that's their frame of reference. They're at rest. They can get out the tape measure and measure it and get a length for that train car or spaceship or whatever. Somebody else, watching it go by and measuring the length as it goes by, will get a different answer. Different by this 1 over gamma factor, where again, of course, gamma is greater than or equal to 1. So the moving length is going to be shorter, usually just a tiny bit shorter, because gamma is very close to 1 until, as we talked about, you get up near the speed of light, but it will be shorter. So we have this length contraction effect. That perhaps raises the question, well, does everything change? Is everything suspect? Are there any quantities that are not suspect? And so that's what we're considering in this video clip. What is not suspect? And in fact, as an aside here, Einstein's theory has become known as a special theory of relativity, or the general theory of relativity later on, just the theory of relativity. And that wasn't his original name for it. He actually preferred invariance theory, that a theory of invariance, because if you actually look at the theory in more mathematically sophisticated ways, more advanced ways, it really emphasizes not the things that change, they're important, but really the things that stay the same from one frame of reference to another frame of reference. So theory of invariance. We talk about what is invariant. So really what we're considering here are a couple things that are invariant from one frame of reference to another moving frame of reference. And actually in the next video clip we'll consider something called the invariant interval, which will be important for us later on. So anyway, let's get back to this. So what is not suspect? We know time seems to be suspect in terms of synchronization of clocks and time dilation. Length is suspect as well. What about other quantities? And in particular, we want to look at the width and height of, we'll go back to our train car here. So here's Bob going along at some velocity v along these super fast train here. And we'll say that the length of his train car is L as he measured it. So that would be the proper length, the rest length of his car as he measures it. Gets out his tape measure there and does that. Here's Alice on the station platform. So this time Bob is moving. Alice is stationary. From her perspective, of course, from Bob's perspective, he's at rest. Alice is moving that direction, to the left, to his negative x direction. So let's look at the perspective of Alice, though. Clearly, from Alice's perspective, she would see this, assuming that the velocity is high enough that you get some gamma there significantly different from 1. So she would measure the length of Bob's moving train car as L moving times 1 over gamma, whatever the rest length was if he brought it stationary, and she could measure it there at the station platform. Then he goes by, she gets a different answer for the length. So now let's consider, let's do a top view first here, okay? And let's consider the width of the train car. All our analysis so far, really, we've been emphasizing just one dimension of motion along the x direction, but we're still emphasizing that as a direction of motion. But let's just imagine we can span it out just a little bit and consider width and height here. So here's the top view of our train car, Bob's train car. It goes along the tracks, some high speed v. And the question is there an effect there? You know, we have a length contraction effect. Maybe as Alice looks at Bob's train car, maybe there's a width contraction effect as well. You know, she gets up on top there so she can see down on top of Bob's car. Maybe there's a width contraction effect as well. So let's imagine there is this width contraction effect. So what would happen if it was a substantial enough effect? Bob's train car would contract as far as Alice is concerned, Alice observing the train car. And obviously, train wheels have rims such that this couldn't happen, but we'll just assume that it's such that as the train car gets shorter, less wide from Alice's perspective, what would happen to the wheels? The wheels would fall inside. Just imagine, you know, the wheels are right here, of course, right there, there, and there on the tracks. But as the train car narrows in width, the wheels are going to be here, and they're going to fall off the tracks. Okay? And if it narrows enough, the whole train car would fall in between the tracks. Right? Obviously, there are railroad ties there and all that. But you get the idea that there would be an accident involved because Alice would see, if there is this width contraction effect, Alice would see the train car get narrower, it'd fall through the tracks that way. Okay? So that's what Alice would see, assuming this width contraction effect occurs. Now let's analyze it from Bob's perspective. Because from Bob's perspective, again, in his frame of reference, he's stationary. He's at rest. What does he see? He sees Alice, you know, shooting back that way, but he also sees the train tracks going by him. Right? In his frame of reference, he's at rest. It's the train tracks that are moving in a negative x direction behind him. He's watching train tracks just constantly go behind him at a high velocity. Okay? Well, if the width contraction effect is true, it has to apply for this situation as well, right? Because, you know, as we mentioned, the length contraction effect, the time dilation effects, they work no matter which perspective, which frame of reference you're seeing here. So in this case, if there is a width contraction effect, it's got to be true for Bob as well because he assumes that he's at rest, tracks are going by him, and maybe you can see what's going to happen here. If the tracks are what's moving with respect to him, and there's a width contraction effect, the tracks are going to get narrower. Okay? So in this case, get rid of these were our original, where the wheels were. For him, the wheels stay the same, his car stays the same, but it's the tracks that are getting narrower now. Okay? So the tracks in exaggerated form. The tracks get squeezed in. And what happens? The train car goes off the tracks, but it certainly doesn't fall through the tracks. It lands on top of the tracks, which are now underneath the car. So you have two very different conclusions. Alice would see the tracks get wider and the train car fall through. Bob would see the tracks get narrower and the train car would come off the tracks but would not fall through. You got to have one or the other. You know, you could take a photograph. They both have to agree on the photograph that it happens. And therefore, the conclusion is that there is no width contraction effect. Okay? That in that dimension, again, it's perpendicular really to the direction of travel. So the length contraction effect is only in the direction of motion. At least we just did width here, and we'll do height here in a second as well. Although another argument you could make here, physicists love to make symmetry arguments, and you could say if there's no width contraction effect, you know, we're going to do height here in a minute. Well, you can just sort of rotate around. There really is no difference between width, height, whatever. It just depends on what direction you choose to be horizontal or vertical or whatever. So if there's no width contraction effect, by a symmetry argument, there should be no height contraction effect either, because you just as easily could define, okay, here's the width, or you could call that the height, and this the width, and so on and so forth. But let's do the actual analysis here for the height contraction effect. And so so that was the top view. We showed that if there's width contraction, you get two different situations in terms of what Alice and Bob observe. They both have to observe the same thing if you take a photograph, and therefore can't happen. Now let's imagine, going back up here to Bob along the tracks, say there's a tunnel coming up here. So we'll just sort of try to draw a tunnel like that. So going into the tunnel. To Alice, the tunnel is stationary. To Bob, of course, Bob is approaching the tunnel. So to Bob, the tunnel is actually coming toward him. He's at rest as far as he's concerned in his frame of reference. The tunnel is coming toward him. To Alice, the tunnel is at rest. It's Bob who's moving toward the tunnel. So let's analyze this situation, and let's assume that this tunnel is just the right height here from Alice's perspective. Okay, that if they were at rest, let's just put the train car at rest there, man. We slowly move it up to the tunnel. We say, hey, it will just fit. So the height of the train car is such that when everything's at rest, it just fits inside the tunnel. Okay? Now, what's Bob going to see, however? Remember, we just did the analysis with Bob, the train car. He's at rest. The tracks are actually moving by him. Bob sees the tunnel moving toward him at a very high velocity. If there is a height contraction effect, okay, so height contraction means height's going to get shorter, Bob's going to be very worried here, scared out of his wits. Probably he sees this tunnel coming toward him at a very high velocity, and if he sees the height contracted, he will see that he is not going to be able to get through that tunnel, or really the tunnel is going to smash into him. Meanwhile, what does Alice see? So Bob definitely sees a big problem coming ahead here, right? Alice sees, Bob, what are you talking about? Again, see, I'm using see in the sense of observe. Okay? Alice observes that there's a height contraction effect, but she sees the train car contracted, because to her, that's what's moving. If there's a height contraction effect on a moving object, it's the train car that's getting shorter. And then she says, hey, Bob, no problem at all. You have plenty of clearance to get through the tunnel. Well, again, clearly one or other thing has to happen when he gets to the tunnel, or the tunnel gets to him. Either he smashes into it, the tunnel smashes into him, or he makes it through. And therefore, since, again, you have this contradiction, you could, at that instant in time, you could take a photograph. You could decide, hey, does he make it through the tunnel? Is it too short? Is it plenty of room, even larger room, more height than we start off with? Again, both Bob and Alice would have to agree on that photographic evidence. So this conclusion is that there is no height contraction effect or a height lengthening effect either. It doesn't go either way, so that height is going to be unchanged. It is not suspect. It is invariant. So when you have motion in one direction, there's a length contraction effect in that direction, but no effects in other dimensions. No effect on width, no effect on height. Those stay the same. So again, that's what is not suspect or what is invariant. And in the next video clip, we'll consider again, as I mentioned, something called the invariant interval that is another quantity that's invariant, not quite as simple as height and width, but we'll see what that is all about.